Morning, everyone. Um, Thanks for staying with us throughout this morning. Um, I promise you the last few techniques we're going to talk about are going to be the most simple and easier to relate to techniques. So please stay with us till the end. Over the last 2 days, we've been looking at analysis of intended particles, liposomes, nanoparticles, suspension drug products. I will take a little bit of a digression where I'll move to unintended particles in our products, especially in parenteral products, specifically analysis of subvisible particles. The techniques we're going to talk about could be used for analyzing of intended particles. So you would see one or two things that are put in there when it comes to its application for intended particles, such as nanoparticles, liposomes, and other drug products. So let's start off by looking at particulate matter as defined by the USP. The USP defines particulate matter as extraneous, mobile, or undissolved particles other than gas bubbles unintentionally present in the solution. That's USP 788. And as you look at the definition of USP 789, once again, we see the word extraneous substance other than gas bubbles. So we're looking at any particle in our product that we do not expect it to be there. It's not part of the product design, but ends up in the product. In general, particulate matter is classified by their size and by their source. When we look at size classification, starting from the largest particles, which you would see with the unaided eye, known as visible particles, then the next set of particles, which we'll be talking about between the size range of 1 micron to 100 micron, form our subvisible particles. Below that, you have your soluble aggregates and your monomer particles, which some of the techniques we've talked about are very good in identifying and characterizing these particles. We would stay in the subvisible particle zone for the rest of this presentation. The common sources of subvisible particles or unintended particles in drug products tend usually to be things like metals, glass particles, fibers, rubber, plastic, cellulose. Sometimes it could be even the drug particle itself, the API particle or the biologic drug substance that is aggregating. Why do we care about the source of subvisible particles? I know most of us might have seen this in the USP chapters already. I threw this in there to highlight the fact that it is not just enough to be able to characterize particles, but knowing the source of the particle is very important in ensuring that we can establish the right control strategies to ensure that our products do meet the quality standards that we do intend to. Source of subvisible particles could range from extrinsic or foreign matter that is not part of the formulation or packaging material or assembly process. This could be fibers, insects, pollen, vegetative matter. It could even come from the personnel, such as clothing fragments, epithelial cells, and hairs. And generally, these particles do not change over time. You could also have intrinsic particles that are product related, coming from your formulation, your assembly process, or your packaging. Examples will look like silicone oil, rubber, metal, plastic, and glass. Instability of the active pharmaceutical ingredients, formulation degradation, or product package interactions. And the last group of particles are inherent particles. Now, this might be a bit quite similar to what you see in the intrinsic particle category. But in this particular instance, we're looking at these particles are expected product attributes that we know and control. Examples are protein aggregates and agglomerates of probably our drug substance. So that it's the bigger distinction between inherent and intrinsic particles, as in the fact that with inherent particles, they expected, we know them, and we have to control. We are controlling the amounts in our drug product. Why do we monitor and even care about this class of particles? For us, our biggest goal in what we do in the FDA is quality, safety issues, right? Increasing subvisible particles can be associated with a decrease in efficacy of our drug products, an increase in risks of adverse events such as immunogenicity, inflammation, phlebitis, and thrombosis. In general, the safety concerns of subvisible particles are related to their size, the type of material, and sometimes the shape. The points listed down here point to some of the impact of the particle size on the type of safety concerns that was raised. Invariable distribution of particles was reported to be site-dependent, with larger particles, about 12 microns, being retained in the lungs, while smaller ones were retained in the liver and the spleen. Particles greater than 10 micron had been associated in vasoconstriction in the past. Small microsphere particles post-injection were taken up by the liver, whilst larger particles were traveling the lungs, irrespective of their nature. Now, this study was conducted in mice. And particles of size 420 to 500 micron were associated with corneal damage, but not particles 300 micron and smaller. This points to the very nature of the safety concerns that is associated with subvisible particles in parenteral drug products, and highlights why we need to monitor and control these class of particles. Beyond our safety and quality concerns, it also raises concerns about how much the product is understood, how much the process is understood, the adequacy of the control strategies put in place, and the adherence to CGMP regulations or CGMP by the company. And this would vary based on the source of particles, right? If you see a hair particle in a product, you might be looking at a different concern than, let's say, if you see an API aggregation agglomeration. So the type of particle here would point to kind of different indicators as to where there's a lack of understanding in the manufacturing process, as to whether there's a lack of understanding in our process, how much control strategy the companies have in place, or how well they adhering to their CGMP considerations. Having talked about the importance of monitoring and controlling subvisible particles, let's go into what our interest in today, which is how do we analyze these particles? The slide on our left shows the efficacy of manual inspection of particulate products particles in our products. Let me see if I can get my pointer here. Right, and as you can see, as the particle size start decreasing, the efficiency in being able to identify these particles do decrease. I would want to point out the fact that the efficiency in determining particles via manual inspection, it's not only dependent on the particle size, but the medium in which the particle is, how long the person has been looking at the particle, the lighting environment, the kind of training the particle do have, and even the particle shape. But in general, there's it's accepted that as the particle size decreases, the ability to identify it via manual inspection becomes very difficult. And that brings the need for analytical techniques such as the ones we're going to talk about in the subvisible particle range. We've heard of techniques such as DLS, AF4, size exclusion for submicron or lower size particles. Visual inspection would do for particles in the visible size range. But for the subvisible particle range, we'll be talking about two techniques, light obscuration and flow imaging, sometimes referred to as MFI. Light obscuration technique and MFI technique. The first one we look at is a light obscuration principle operation. Light obscuration, as the name sounds, the particle blocks or obscures light as it passes between a laser and a detector. The cartoon on our right illustrates that for us. As a particle passes through the sample cell in between a laser and a detector, we have an output as the particle blocks the light. Now, this output is what it's converted to our particle size using an already calibrated calibration curve based on polystyrene beads. Light obscuration, sometimes also referred to as light extension. The amplitude and the number of photos generated are dependent on the size and the particle. So there are two basic informations we get from this technique. The number of particles, each time a particle goes through in between the detector and a light source, we have a count being taken. And then based on the intensity of the pulse height we get over here, we can also determine the size of the particle. The size ranges that is usually detected or quantified by this technique is between 1 to 300 micrometers. Let's look at the technique one more time. We have particles moving through a sample cell or region of interest. And as the particle goes through, they obscure or block the light. A photodiode converts the amount of light obscures to a pulse height distribution. And based on an already calibrated, already applied calibration using polystyrene monospheres, we're able to get our size distribution in equivalent circular diameter. Now, using simple statistics, this raw data could be converted to other weighted distribution. But I would say we would not want to be looking at this kind of statistical converted distribution, but be looking at the raw data in terms of the count or the concentration and equivalent circular diameter. Recent advances of this technique have used more than a single detector. In addition to our extension detector, we could have some of these instruments that you have a scattering detector added as well. So it's not only measuring the amount of light that is being extinct or obscured, but the amount of light being scattered. The rationale of the goal for this is to be able to extend the particle size range at which you could use this instrument for. That is now extended from between 1 to 300 micron to particle size as low as 0.1 microns. Before we move on to the step, next slide, I want us to take a minute and really look at the configuration of the instrument and think about what could really go wrong with the instrument when it's being used. Usually, I think it's very easy to relate to results we get from an instrument where we really understand the basic principles of how the instrument operates. So we have a cell, a flow cell, where our particles is passing through. As it blocks our light source, we can get our count. And then based on the intensity or the pulse height that we can get our results. So if you're looking at the things you want to look out for this instrument to ensure it's working as it should be, the first thing you'll be looking at is how much volume is flowing through per time, because we're counting the number of particles per time or volume. So some of the things to look out for when it comes to calibration of this instrument is the instrument's ability to measure the exact volume that is going through, right? The time that is being measured, if it's a time-based sensor. These are the things you want to look out for to know whether the instrument is appropriately calibrated or not. In the past, where lasers were not very great, you could be looking at the lifetime of the laser, but these days lasers do really last a long time. So the lifetime of the laser might not be as great a factor. Another thing you want to look out for is the fact that are we really getting the size that we do intend? As I mentioned earlier on, we are applying a calibration curve that is using monospherical polystyrene particles. Unfortunately, most of the particles that we would do encounter in our pharmaceuticals products are not going to be of the same shape, size, or refractive index as our polystyrene. So how well it's our calibration curve telling us the size of our particles becomes something that we would have to be interested in, which is the size setting error. The last thing you could also think about here is, can we really count every particle that is going through our product? That is called the calibration efficiency. Usually you want to have a system that can get at least about 90% of the particles that do go through the system. I did bring this up here because I believe that really understanding how the system operates makes it easier to understand or deal with most of the challenges we would see when it comes to the data or the results we get from companies when it comes to some of these instruments. Now let's go on to the next slide and look at some of the common vendors or types of light obscuration instruments. One of the most popular ones, the HIAC 9703 LO instrument. We have the APS 2000 sampling system, the PAMAS SVSS, and the syringe by Clos. The most, we do have this available in our lab, the Acquisizer STOS. But these are the different types of vendors or different types of instruments that you would see when it comes to light obscuration. The principle of operation do not change between the manufacturers. What might change would be the syringe pump size, or either the addition of more detectors to expand the calibration range of the instrument. The principle is quite similar and does not really change between instruments, making it quite easy for the data for you to kind of switch in between instrument manufacturers. But in that case, you would want to do requalification of the instruments to make sure you have your method well transferred. So let's look at the advantages. I think I did mention some of them in the previous slide. It's a very well-established technique. It's recognized by the ISO and USP as the primary method for measuring the size and number of particles in the products. Very easy to use, high familiarity in the industry. You need it involves a limited operator error because of the ease of use, and it's quite easy to interpret the data. You have your number of count, which corresponds to the number of times the light source is blocked, and the equivalent circular diameter that you do get by using the calibration curve, which is in the instrument already. Your particles are being directly observed in solution, rapid analysis, the result is in second, medium to high throughput, and very little or no consumables is required. However, just as every instrument do have some limitation, this instrument do have some limitation. For this instrument to work well, you want a single particle passing in between our light source and our detector. So sometimes you might require dilution of our samples, especially when it comes to looking at particles which are intended in the product. Also, if you're looking at particles lower than the 5 micron size range, you might run into a place where you probably might need to dilute it to be able to have a single particle passing through the detector at a point in time. However, we should be aware of the fact that dilution of our samples may change the sample properties, and I will talk more about that in later slides. The upper limit of the particle load depends on sensor use, and there's a potential for coincidence counting. Just as the multi-scattering that we talked about in other techniques, if you have more than one particle going through there, you are going to end up having a lower particle count than intended. Some of the older versions of these instruments are prone to clogging because the flow channel could get physically blocked. Another important consideration is the instrument is very sensitive to air and gas bubbles. And so when you're having data from products such as reconsidered lyophilized product, amphiphilic molecules, you want to be careful about how you do analyze it. It's always important to degas before you do sample analysis. However, the degassing technique can change sample properties. Once again, that's another topic I think I'll go on. I'll add more to it in the next slides. Unfortunately, light obscuration cannot distinguish between different types of particles. In our earlier slides, I mentioned the importance of knowing what particle we are measuring or we are counting, right? If you want to be able to control the presence of these particles in a drug product, it is not just enough being able to count it, but we should be able to know what particle it is and be able to distinguish between the different types of particles in our product. Unfortunately, light obscuration do not provide information on the origin or true presence of particles in what we are testing for. The results are in circular diameter. Once again, we are assuming that the ability of a particle to extinguish light is similar to that of a monospherical polystyrene bead. And so we might have some inaccuracies for non-spherical particles. Accuracy and productivity is quite low for 10 particles count of 10 lower than 10 particles per ml. And so when it comes to some of the data you would see from this instrument, it will not be surprising to see RSDs as high as sometimes 25% relative standard deviation because of the limited accuracy at lower particle counts. It may undercount particles in high concentrated biologics. It may undercount particles with low refractive index, and the sample cannot be reused again. So let's go into detail some of the limitations and some of the things we would have to look out for when it comes to the technique. First thing I did talk about was coincidence error, when you have more than one particle at a time in that measurement zone. Now, on our left figure on our left, you see a single particle passing through our measurement zone at a time. Now, when you have more than a single particle going through at a time, we have what is called a coincidence error. And what this will lead to is you are definitely going to undercount the total number of particles in your drug product. When you have 2 or more particles in the measurement zone, you have a coincidence error. It also depends on the speed of the particles versus the speed of the pulse height analyzer, right? How quickly our instrument is able to convert our pulses to a particle count would also affect the risk or the potential of having coincidence error relative to the speed of the particles. The figure on the right there, you see that as the particle count goes high, we start to have a drop in our measured particle count because of coincidence error. Different instruments have different upper limit for coincidence error, ranging from as low as about 24,000 particles per ml to as high as 120,000 particles. The most common system, the Acquisizer system, have a coincidence upper limit of as low as 15,000 particles per ml. One would say, why should we really care about this? Because if you're looking at that USB specifications, we're looking at not more than 6,000 particles in the lower size range of greater than 10 microns per our container. So the risk for having this error is quite low. However, when you go to products such as biologics, where there's quite an interesting particle size less than 10 microns, you might run into the issue of having more than 15,000 particles. Sometimes particle count as high as 10 exponent 5 per ml in a product. And in that instance, this becomes an issue or a challenge, limiting the applicability or usefulness of this particular technique. So yes, in particles of count greater than 25 micron or even 10 micron, you might not be too bothered about it, but if there's a concern or the need for the company to characterize particles between the size range of 2 to 10 micron, now this becomes something that you would need to look out for. Another thing that we want to look at is the impact of air bubbles. Forgive me for my busy slide, but I want you to focus on the things that I've kind of highlighted in these slides. Let's look at the figure on our top left. This is a live oscillation analysis of a particle with and without foaming. Now, the foaming was induced artificially to look at the impact of air bubbles on our counts. And as you could realize, without any foaming and with foaming, we have almost a five times increase in our particle count greater than 10 microns. Similarly, the particle counts greater than 25 micron went up a little bit. In the second product here, Tagoset solutions, the same effect is being seen with and without foaming, which is induced by how the sample is handled before analysis, right? You are mixing different samples to get, let's say, your minimum requirement of 25 ml. You're transferring in between vial to your container. You could induce foaming or you could induce bubbles, and that could cause a similar error where your particle counts tend to be way higher than what is expected. In this instance, we see an increase in both the particle counts of particles greater than 10 microns and that greater than 25 micron. To understand the properties of the product and the risks of this particular error, an example was done using SDS, which is factor, meaning it has a high risk of forming foam or bubbles during handling. And as you could see, as the concentration of our surfactant increases, so that the count of our particles will be accounted. The image here shows us that, yes, it's the bubbles that is being counted and not actually raw particulate matter in our product. This is a very important consideration when it comes to light obscuration analysis. And so you want to ask yourself, how was a sample handled or the gas prior to analysis? Some of the most common approaches to the gas on the sample would be just letting the sample sit with time and analyzing the sample when you have a lower level of bubbles in it. And here you could see that the number of particle count is decreasing. However, with the same sample, when you use vacuum degassing, we've moved from as high as 681 particles per ml to as low as 51 particles per ml, right? So the risk of having false positive is very high with this technique. The USP suggests that you could use sonication for reducing degassing. What I would say is anytime you see any method using sonication, you want to get your lenses and your eyebrows raised, because based on the stability of the particle, you could end up causing degradation of the particle or change in your particle counts artificially. And so sonification most of the times is a no-no unless there's a demonstrated, the company demonstrate that the particles are quite stable through sonification. The next practical consideration that we want to look at is a sample contrast or refractive index. The ability of a particle to obstruct light is a function of the particle's optical contrast. When I'm talking about optical contrast, what I'm referring to is the difference between the absolute refractive index of the particle and the aqueous solution or the medium in which the product is in. As this contrast or as this difference lowers, the ability to accurately count the particles decreases. Light obscuration may undercount particles with low contrast. The particle count noticeably is affected when the difference between the refractive index of our product or our particle of interest and our medium or our environment is less than 0.1. We see more significant effects when you're looking at difference of less than 0.05. One may say, well, it's easy to just look at the refractive index of our particle compared to our medium and determine whether this risk is high or low. Unfortunately, it's not that simple and straightforward because it's not easy to determine the refractive index of a particle, right? We're talking about a particle, not a solution. The easiest way would be to do some primary testing where you kind of maybe change the refractive index of the medium and see if the performance of the instrument or your accuracy is changing. So that will be the most practical approach rather than looking at just comparing the differences in refractive index between your particle and your medium. And this data here, I don't have the reference, sorry about that, really highlights the challenge of the similarities in refractive index between your medium and your particles on your ability to accurately count your particles or determine the counts in your product. So this here was using light obscuration to determine or quantify the number of polystyrene beads and glass particles in a buffer solution in a highly concentrated mono and clonal antibody solution of 60 milligram per ml and a similar product at low concentration. And let's just focus on the highlighted things and not everything on the slide here. But as you can see, when looking at the polystyrene beads, when you're comparing to where you have a buffer to a highly concentrated monoclonal product, we have almost a 13% drop in the number of particles we are counting, right? Highlighting the impact of refractive index or sample contrast in our ability to accurately quantify particles in our products. Looking at glass particles, we have similar effect, but in a low concentration or low concentrated product, where we have almost a 9% drop in the amount of particles we are counting. Now, this do highlight the impact of our sample contrast or the difference between our refractive index of our particle and our medium in the accuracy of light obscuration measurements. Some additional practical considerations when we look out for a sample viscosity. Right? If the sample is highly viscous, it's likely to affect the accuracy of our measurements due to two reasons. It might impact the flow rate. For us to accurately quantify the number of particles per ml, our instrument should be able to tell us our flow rate accurately, right? One of the things you do during calibration is a flow rate test. You have a flow rate sensor to make sure the flow rate the instrument is giving is actually exactly what is being measured. When you have a highly viscous sample, you might have issues with your flow rate because of the increased work or the load of your motor. And so you could have errors because of the issues with flow rate. It could also be due to poor contrast, right? High viscosity, you probably will change the refractive index of your medium. You end up having a poor contrast. And so with highly viscous samples, especially highly concentrated biologics, you might have higher than normal error frequency. Similarly, in opaque products, older instruments tend to have issues. And in both instances, you probably might need to dilute to alleviate the effect of viscosity and color samples. Per the USP standard, your first option would be to do microscopy. If you're still having the challenges, then you would have to dilute. However, dilution of samples for light obscuration is still allowed. In dilution, it's important to look at the impact of dilution on your particle stability equilibrium effects. So let's say I have a biologic or I have a product in which our agglomerate is not highly stable, right? It has an equilibrium reaction between our monomers and our dimers or our trimers or higher molecular weight substances. Once I dilute the system, I could have a change in equilibrium effect where we have a movement from higher molecular weight products to some lower molecular weight species or monomers. And in that instance, I have artificially changed the particle count in my actual product. It could also be due to refractive index changes. You diluted, you also change in the refractive index of your medium, and that could also work against you. The best approach or the recommended approach is, as if needed, you want to use the minimum dilution, but you also want to make sure you're working within the linear response, meaning you want to look at a calibration, you want to look at the impact of dilution on your count. If your dilution at a certain level is not giving a linear response, it means you really cannot use that in estimating your particle count in your actual product. So I think I've been talking for the last 30 minutes. So let's take a quick quiz here and see if we are all following the discussions that the things we're talking about here. Which of the following sample parameters can impact the accuracy of size measurement by light obscuration? Please put your answers in the chat. Let me see if I can see the chat here. I'll wait for a few more, then. Okay, most of you are giving the answer is D, right? It's the particle shape. When I talked about particle shape, I referred to the fact that we have a monospherical particle being used as a calibration standard, right? The monospherical particle ability to obscure light would be independent of the shape. It will be the same independent of where the orientation of the particle. Unfortunately, based on the shape of the particle or the aspect ratio, some particle would have different abilities based on their shape when it comes to the extent to which they're able to obscure light. You could also have orientation effect, right? Based on how the particle is oriented, the amount of light obscuration would change. Refractive index, we have talked about it and its impact on contrast, and a particle concentration. Very low particle counts, your high error margins. Very high particle counts, you run into the effect of having more than a single particle going through your measurement zone at a time, and then you could be undercounting your particle. So great, most of the answers were right. So let's move on to the next question. Which of the following instrumental parameters needs to be routinely calibrated to ensure the accuracy of light obscuration? Let me clarify this question here. I think per the ISO standard, routinely might be about once a year. So which of these parameters do you think it's worth calibrating or it's worth checking to make sure your instrument is performing as you would expect it to be? I'll wait for a couple more answers and then we would see. So this was one of the questions that we did not have a lot of slides on that. So I'm not surprised I'm getting a mixed answer between B and D. The correct answer would be D, right? Our counting efficiency, how much of our particles passing through our measurement zone is our detector being able to pick up. On the average, you want your instrument to be able to pick about 90% of that. The sampling volume and flow rate error is something I think I've talked about considerably, because if you want to actually quantify the counts per volume, then we want to know the volume or the flow rate going through at a particular point in time. So we would need to, once in a while, annually, per IO specification, make sure that our instrument's pump is working as it is. Is our instrument really measuring the size and resolution we want? Yes, for us looking at particles just generally greater than 10 micron and 25 micron, you might not care whether the particle is, let's say, 40 micron or 50 micron. So yes, I understand why most of you are choosing D, but the sizing error, it's important in the fact that you also don't want your instrument giving your particle size at least 10% of the actual particle size. So is the instrument calibration working as it's supposed to be? Is it giving you 10% off or 20% off? So it's an important parameter to calibrate for. I'll show in something here that raises concern when it comes to particle analysis, what type of standards we are using for calibration. It's not a topic we are discussing today, but I think it's something we'll have to think about the more going forward, especially when it comes to products like biologics, nucleic acid-based products, and other complex products. Because if you're using a sphere for all your calibration, and then you're looking out for particle, even less a glass particle, very different characteristics from your calibration. So like, it raises the question, how really valuable is your calibration standard? I think it's something that is really going on in the particle size community, especially as it pertains to biologics, but it's something that I think all of us would have to think about going forward. Let's go to our next technique, flow imaging analysis. I think it's referred in some quarters as dynamic flow analysis or dynamic flow imaging. USB flow imaging analysis, what is used. So that's what I'll stick to in the last part of our presentation. So what is it? Let's look at the basic. What is it? Simply put, what you do have is a digital camera, high optical system, your flow cell, and where you have a detection zone and your light source, right? So you have your samples or your product flowing through your flow cell. And using an optical camera, you take images of these particles, and then you analyze the particles based on what you get from your image. A high magnification imaging technique for analyzing surface of particles as a pass-through a thin flow cell. So you have two main components of this product, your fluidics component and your imaging component. The good thing about flow image analysis is we are not only getting the particle size, but the particle morphology. We'll look at how the morphology is obtained from the image in our next coming slides. The working range is 0.1 to 100 micron. Let me correct that. Based on the flow cell you're using, you could go as high as 300 or 400 microns for size reading. But when it comes to morphology, the lowest particle size range we can accurately quantify its morphology or detect its morphology is between about 4 to 5 microns. Once again, this cartoon helps us have a very simple look at how it works. We have our digital camera with the optical system, our flow cell where our sample is flowing through that, and our light source that's from mass illumination. You can introduce your sample either through a pipette, a syringe system, or by a manual pump system. Image acquisition is quite at multiple frames per second. So as your sample is moving through your flow cell, your camera is taking multiple images per second. How frequent the images are being taken would impact the efficiency or the percentage of your total volume that you did actually count. You detect your particles, and you have an image of your particles from your camera, and from that, you could obtain your other characteristics such as your counts, your concentrations. You could do trend analysis. You could look at different classifications based on not only the size, but once again, the morphology of the particle or the images that you do obtain. In terms of size range, we've seen this again, we're looking at quite a similar size range as we did talk about for light exploration, from about probably 1 micron to as high as about 300 micrometer. That's the size range we are looking at. For morphology classification, we're looking at lowest particles morphology of about 4 or 5 micron. Our particle size is equivalent circular diameter for flow imaging analysis. These are the two common vendors or instrument types that you see: microflow imaging from Protein Simple and FlowCam 8000 from Fluid Imaging Technologies. We do have both techniques available in our labs in Building 64. You are free to stop by to have a look at it if interested. Let's take a closer look at the instrumentation once again. As I said, we have a fluidic compartment and we do have an imaging compartment. So we have a pump system that allows us to move our fluid through our flow cell. And where our flow cell is, we would have our cameras, we would have our light source to be able to take images, but also give us the right image contrast or lighting system for our particles. On the left, it's that from the MFI. On the right, it's similar from our flow cam. We have our fluidic system, our syringe and our pumping cell, our flow cell, where we are detecting our particles, but right by the flow cell, you see our optical system, which is our cameras and our lighting system that takes multiple images per second as our samples move through our flow cell. So as you can see, this is quite a very simple technique in terms of how it does operate. These are images of the different flow cells that come from different manufacturers. On the left is the MFI flow cell. On the right is the FlowCam flow cell. This has an outer membrane, but in there you see a much more thinner flow cell in there where we're taking our images. One thing I would want to point out is all these manufacturers have different sizes of our flow cell. As you change your flow cells, because we have a camera system, it would impact your field of view. That means it would impact your efficiency or the number of or the percentage of your total fluid volume that you are taking images of. So some change, if you are changing your flow cell, it might be calibrating the instrument. But flow cells, it's the location at which we're taking our images. And it's, I'll say, one of the workhorses or the parts of the instrument that needs to be well paid attention to. What is the size of the flow cell that is being used with respect to what its efficiency or what percentage of our fluid we are taking images from. So how does flow imaging compare to the other USP techniques such as light obscuration and manual microscopy? In general, when you use flow microscopy or when you have data from flow microscopy, you are going to have higher particle counts than you get from light obscuration and manual microscopy. This tells us about the efficiency of the system in detecting particles compared to the other two techniques. It's been reported in the range of 2 to 10 times differences in particle count between our flow microscopy and light obscuration. And this difference generally might stem from the fact that our flow imaging technique might not be as affected by difference in the contrast between our particle and our medium as much as light obscuration is affected. Flow imaging is more sensitive than light obscuration detection of translucent protein aggregates. It's less affected by the closeness of refractive index of sample and solvent. We provide size and morphological data. The morphological data allows multi-parameter filtering, which allows us to discriminate between inherent, intrinsic, and extrinsic particles. Example, silicon oil droplets can be distinguished from protein aggregates. This is the specification from the MFI given as our concentration limits, sampling efficiency, and image acquisition rate. As I said, the image acquisition of frames per second that is captured impacts our sampling efficiency. And then we have our concentration limit. So if you compare this to a light obscuration, realize that we are looking at about almost 900,000 particles per ml as compared to only 15,000 particles per ml in our size range for light obscuration. And the maximum volleyball is way higher at the lower concentration. As I mentioned, when you're looking at biologics and other products that are prone to forming aggregates of particulates, inherent particles, usually you're going to have very high count of particles of size smaller than 5 microns. And in there, you have a big limitation when it comes to light obscuration because of the issue of coincidence error. This would have the lower risk of coincidence error. However, you still would have to think about coincidence error even when looking at this. It's how many particles are in the image. Is a particle hiding behind another particle? The risk is low, but it's not something you could completely discount. So let's take another quiz here and see if I'm getting the points across carefully or well. The accuracy of particle count by flow image analysis is not affected by the similarity of the dispersant and particle refractive index, true or false. I'll wait for more answers, then I'll move on. Yeah, the correct answer is false. I think most of you probably got it right, about 99% or 95%, just throwing out a number. The impact of sample contrast on flow imaging, it's lower than light obscuration. However, we cannot discount that impact on the accuracy of our concentration of particle sizes we do get from this technique. Okay, so let's move on to the last part of our presentation. So this, I talked about, in addition to our size, we do get morphological data. The morphological data comes from the fact that we do have actual pictures or images of a particle, right? On the top, we see how protein aggregates look like. We have our PLG nanoparticles, silicon oil droplets, glass particles, air bubbles, plastic, and rubber, right? So based on how the particles look like, it's very easy to distinguish between inherent particles, extrinsic particles in our products. That's an added advantage that we do get with flow imaging that we don't get with our traditional light obscuration technique. And this chart here gives us some of the morphological parameters or filters that we do get our flow imaging. I'll go through how some of them are calculated or determined, but this is just a few of them. There are way more than that. That there are different morphological descriptions or filters that we could get from our image, right? We could calculate different parameters from the image we get. And then based on that, we can use the combination of different filters or parameters to distinguish between the different types of particles based on either the area, based on how the image looks in terms of the intensity, based on the parameter, the circularity, the aspect ratio, the Fourier diameter. It allows us to have countless number of parameters and gives us the ability to, in a way, identify the source of our particles in our product. The first parameter that is calculated is the area. This is what most of our parameters are based on, even the size. This is done by what is called a threshold, right? So you have a grayscale where it looks at pixels or areas where there's a minimum threshold of grayscale we're looking at. So far as there's some pixel or there's some, it's above that expected grayscale, we count that pixel as part of our area. So these are binary scale of areas or pixels with or without part of the object. And you could see here, it does to correspond to the various small pixels or boxes where our particle is. And so based on the area we get from the sum of these different areas, we can determine our equivalent circular diameter, right? Based on our area, we can calculate our ECD. The diameter of a circle that occupies the same area as a particle. We count the pixels to find our area, you convert to circle with equivalent area, and then you estimate your equivalent circular diameter. So this is how the technique estimates the ECD or the size readings from our products. And as I said, there are different parameters that the instrument could estimate. I will not go through that, but these are simple reads that you can look at. You can look at the maximum Faraday diameter, which is the largest distance between two pixel corners in a particle, the aspect ratio, the circularity, the intensity, a value of 0 for completely black, and a value of 1023 usually for a completely white product. Now, based on the variation intensity mean, the standard deviation, the maximum and the minimum, you could use that as a parameter to distinguish between the different types of particles you do have in your product. So example, let's say we have a product that has silicon oil in there and protein aggregates, right? We want to know what percentage of our particles in there are protein aggregates and what is silicon oil. Silicon oil is usually used as a lubricant for our syringes, peripheral syringes, and even sometimes in regular glass vials, we would use it as a lubricant for the stoppers, and allows us to easily, what we call machinability, machines be able to easily pick them up and then seal our products. However, there are times you could have more than you expect in terms of quantities of silicon oil getting into your product. For biologics, the danger of silicon oil being your products, it can induce aggregation. So you'd want to control that, right? You can only control the levels of silicon oil in your product or how much you use for lubrication if you can accurately quantify what is in your products. If you are to use light obscuration for this particular technique, your chances of not being accurately being able to tell what is silicon oil and protein aggregates is very high. So in here, using a simple parameter or filter as an aspect ratio greater than 0.5, you can, in a way, about 80 to 95% of your silicon particles be qualified or quantified because of the difference in the aspect ratio between our silicon oil and our protein. There are times it gets a little bit more complicated than just a simple parameter. You might need to look at a series of morphological parameters and pick a combination of parameters that allows you to very accurately distinguish between your particle types. If you look at our ECD for these three different particles, they are quite close to each other. So we cannot really use that to separate or distinguish the types of particles we have here. But then as we include more morphological parameters, we do have more chances of being able to accurately quantify the individual components of our particulate system in our product. Some practical considerations. We are taking the images in our flow cell, right? If our flow cell is dirty, it's going to affect the quality of the images we're going to get. That means it's going to affect the interpretations we make from our results. So one of the first things you want to look out for is the flow cell clean? What is the integrity of the flow cell? There are times you could have some particles sticking on the flow cell. Now, if you have that happening, you might end up counting the same particle over and over again, and you might have a higher than expected particle count. Some of the instruments allows you to be able to eliminate that in your analysis because of the position of the particle in terms of the X, Y, and Z as in the images. But it's something you want to look out for. You could have flow cell fouling where particles do stack to your flow cell, and then you have high margins of error. So for that reason, it's important to keep the flow cell clean. You want to clean it before and after analysis, and you want to change it after a certain number of runs because you are going to lose some of the interior coating and then high rates of particles stuck into your flow cell. We're dealing with the imaging system, so how you focus your particles is very important. You could see in the middle here, very sharp image, but then as you look at the blade image, you could see some components of our cat is missing. The cat here has no whiskers, right? The sharper the images, the better our ability to determine that size, but also the morphological parameters of our product, of whatever is in our product. You could see below here in this figure here from Protein Simple, how changes in our focus do affect our ECD or the mean ECD that we are measuring. In the right position, we have about 10.1, but 10.1 for our ECD or size, but it could be as high as about 10.8 or 10.9 if we are out of focus. So proper alignment of our optical system before each analysis is an important thing or important consideration. Purging our system in between runs. We don't want to have particles from our previous run interfering with our current run. But at the same time, we have to be careful how we do clean our systems, right? You want to make sure your flow cell is adequately cleaned up, purged, avoid mixing effects, false particles, or slurring lines. I will explain what that's in the next slide. That's a simple way of determining your flow, how much volume you really need to page your system in between runs. You can look at how your particle count is changing with time as you flash it through your fluid cell. That will give you an idea, at least the minimum volume you need to page your system. The MFI system will have an additional function that is called the time resolved analysis or the trend chart. With that, you could just run that and it would accurately tell you how much or the minimum page volume you do need to be able to make sure that you don't have mixing effects or false positives. I then mentioned slurring lines. Now, what does usually mean? What this means or when this occurs usually is when you have an incompatible page and sample fluids, right? Especially differences in viscosity or refractive index. Your sample has a different refractive index than what you're using as your page fluid. And so you will have them not really mixing very well at the start and end of the experiment. So that's how your flow cell is going to look at. So meaning there are going to be certain times in your experiment where the image being taken do not accurately reflect what is in your product. So it's not acceptable in the presence of slurring lines. It's important that you make sure that your page fluids and your sample fluids are quite compatible. We did talk about impact of bubbles on light obscuration. Unfortunately, we do have the same effect when it comes to flow imaging technique. And the figure on the left shows that before and after degassing, you see how much difference we are seeing in particle size of particles greater than 2 microns. So yes, the impact of gas bubbles on the accuracy of analysis, it's also an important consideration even for flow analysis. You have to degas your bubble-prone solvents and products before use. Vacuum degas, no sonication. But what I would say is avoid sonification at all costs if it's possible. If a company is using sonification, you want to see data ensuring that sonication is not degrading your particles over time. It's not suitable for protein aggregates and unstable agglomerates. Some of the sample considerations, we're looking at particles dispersed in a liquid medium. That's what we are measuring. The displacement refractive index should be different from the particles of interest. Ideally, it's important to use the same sample fluid as a page fluid to avoid slurring lines. Sample viscosity can also impact your accuracy. Now, if the sample's viscosity change, and it's important that you want to make sure that the pump system is calibrated with the same viscosity of that product to make sure that we are not in any way having an error because of load on our pumps. We want to stay below the viscosity of less than 20 CP. Degradation of particles can occur over time. So having a time resolve mode, especially with MFI, allows us to kind of do a quick check to see your stability of your particles over time, making sure your particles are not degrading as it's being pumped through the system. Particle concentration in excess of your maximum limit will lead to coincidence effects. This might not be as high an issue as in light obscuration, but once again, it's something we have to look out for, especially when you're looking at particles less than 5 micron. Samples with low particle concentration may require more samples. Yeah, obviously you need more samples to make sure that you're getting a good representation of what is actually in your product. Colored and turbid samples may lead to error, meaning you might need some dilution. And once again, the gas bubble-prone solvents. You're looking at lyophilized products or lyophilized products, looking at products with highly concentrated biologics. It's important that they are degassed, typically by vacuum degassing before the analysis. This general considerations apply not only to flow imaging, but also to light obscuration. You want to work on the laminar flow hood, right? You want to eliminate the fact that the particles you're measuring are actually what's in the product and not from your environment. You want to flash your system with excess fluid to avoid drying. You don't want the system to dry over time. You place your inlet fluid. This really goes to maintenance of the instrument, and I think it's something you could read or look at over time. So I wouldn't bore you with every single detail of that. Some of the limitations, we talked about the minimum particle size morphology analysis. Most of our results is dependent on our algorithm, as you could see. We're taking an image, converting that into a grayscale and a binary scale and using that to determine most of the output. So that is a limitation based on how you look at it. It's difficult to visualize particles with low contrast. Sample dilution may cause changes. And once again, sensitivity to air or gas bubbles. I'm thinking this might be our last question. Which of the following parameters may affect the accuracy of flow imaging analysis? Which of the following parameters may affect may affect the accuracy of flow image analysis. This is not a trick question. Flow still clean, that's right. Yeah, most of the answers are right because almost everything I have that can affect the accuracy of the results. There should have been one last option, which is all the above. Particle orientation might not be the biggest thing, but it could also still affect it because based on the rotation of the particle, you probably have a different image. Cleanliness and focus is a very important thing. Sample viscosity, we did talk about how it could impact your pump and the accuracy of the fluid you're moving through. And we could get the correct answer or your frame rate, which would affect the efficiency or how much of your sample you are actually analyzing. Thank you all for your answers. So these are the references, and I think I'll pause here and take any questions. I think I saw a question about silicone oil for elastometers. Yes, sometimes it can be used, not as frequently, but yes, you could use that to make sure that you don't have issues doing stopping of your glass valve. So that's also that sort of silicone oil. And I have a question about pixels. I think I don't have it offhand. I should get it for you after the minimum size of the pixels. Any more questions, comments, clarifications? Okay, thank you so much for your time. Janet and Sherman, I think okay, what is the optimal volume of sample? You could go as low as 150 microliters for flow imaging based on the configuration of your syringe and your pump system. If you want to use the automated system where you have a robotic system running it, then you're looking at about 1 to 2 ml of sample. But because of the cost of products such as biologics, recent advances allow you to use as low as about 200 microliters for analysis. Okay, Sherman and Janet, I'll hand over to you. Thank you all for your time.
Thanks, Max. Thank you everyone again for staying around for the second day. So we have tomorrow, the final day. So in the morning, tomorrow morning, I will start with talk about the some of the considerations in the during the method validation, which I think you may find very interesting because that has to do with a lot of things you might find in the review. And also we'll talk about some of the common deficiencies we have seen based on our experiences. And then we will tomorrow have a breakout session. Hopefully it's going to be fun for a lot of you. So yeah, so let's close out today's training. Thank you everyone again, and see you tomorrow morning.
Thank you. Bye.